Hello, Tim Stark. Are we ready to get started?
Yep.
Hello, everyone, and welcome to today's webinar, Stability of Geosynthetic Line Slopes Part 2, brought to you by the Geosynthetic Materials Association and the Fabricated Geomembrane Institute. I'm Andy Durham, GMA Executive Council Member and Geosynthetic Engineer at Owens Corning, and I will be your moderator today. GMA provides engineering support, business development opportunities, educational programming, government relations expertise, and industry recognition. GMA influences specifications and lobbies on behalf of member companies and targets key U.S. states to expand the geosynthetics market. GMA also provides a network to exchange information, solve common problems, and develop mutually beneficial relationships. Fabricated Geomembrane Institute is an industry-sponsored nonprofit institute dedicated to advancing the use of fabricated geomembranes through education, research, and technology transfer. The FGI is housed at the University of Illinois at Urbana-Champaign in the Department of Civil and Environmental Engineering. Fabricated geomembranes are used in many applications such as floating pond reservoir covers, landfills, golf course water features, industrial waste ponds, canals, mining, coal combustion residuals, oil and gas, water and wastewater containment. Our members are manufacturers, fabricators, installers, engineers, service providers, equipment manufacturers, and raw material suppliers. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions box of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. The recording of this webinar and the PowerPoint will be made available after today's presentation. I'd now like to introduce our presenter. Dr. Tim Stark is a professor of civil and environmental engineering at the University of Illinois at Urbana-Champaign with an expertise in geotechnical engineering. Dr. Stark has been conducting research on geomembranes and other geosynthetics for over 20 years. He's the technical director of the Fabricated Geomembrane Institute at the UIUC. Please welcome Tim.
Thanks, Andy. Good morning, everyone. Thanks for joining Slope Stability Part 2. Today, I will focus on slope stability analyses, calculating factor of safety, in particular for unreinforced and reinforced slopes. The main topics today are listed here. So first, factors affecting the stability of geosynthetic line slopes. It can be summed up in a simple expression: load the top and cut the toe. Those are the two worst things that can happen to a slope. With those other driving stresses and shear resistances, we can calculate a factor of safety by dividing the resistance by the driving forces. Some of the driving stresses are highlighted on the screen: steep slopes, high unit weight materials. And our shear resistance comes from the geosynthetic products we install, as well as some geometrical factors we can include in the slope, such as toe support in the form of a buttress. So the next topic is critical cross-section. Before we can calculate a factor of safety, we have to determine the critical cross-section as well as the critical failure surface, and then we calculate the factor of safety for that combination. So critical cross-section first. Here's a plan view of a landfill that was analyzed using the cross-section that I'm highlighting with my pointer. That was selected as the critical cross-section for this particular facility. However, you can see in where the cross-section is drawn, there's actually a three-dimensional curve or a concave portion of the slope right where that cross-section is oriented, which makes that actually a stronger slope because of the three-dimensional effects. I'll end the webinar talking about three-dimensional slope stability. So if you wanted to find the critical cross-section for this particular facility, you would move this cross-section to maybe this corner where my pointer is, because first of all, the contours are fairly tight on the slope, and these horizontal lines here are contours. And also there's an excavation at the toe of the slope. So that's cut the toe and load the top. Other places you might check the factor of safety are along this side. These contours are fairly tight, as well as maybe this side on the left. Generally, the nose of the facility right here tends to be a little flatter than the slopes along the sides because the nose sticks out a little further and thus the angle of the slope's a little flatter. So that's one example. Here's another example of a waste containment facility. You can see there are a number of places you could draw a cross section and calculate factor of safety. But let's look at some places where you have a three-dimensional effect and a fairly high factor of safety. For example, right in this area, you see there's a notch into the slope. So there's a three-dimensional effect holding this portion in. Here's the nose of the slope. That's a little flatter, but that's a good spot because you can see a fairly long and steep slope. Another area is over here where my pointer is. And so you would check the factor of safety in these various areas. Here's another facility with a excavation at the toe and the slope rising above it. Here's some people for scale there. A firm analyzed the stability of this facility and cut a cross section through the corner. That again has a three-dimensional effect on it, and the 2D factor of safety that you calculated is underestimating the stability of the slope. You would move the cross section over further away from the corner, maybe in this area, so the toe would daylight into the excavation. Critical cross section. There's one critical cross section for each facility or each slope. So text like this from various consulting reports really don't make too much sense. For example, 3 of the 5 critical cross sections selected for slope stability analyses, selection of the most critical cross sections for slope stability analyses. A total of 3 critical slope sections were analyzed. And then finally, when we do get to talk about factor of safety, this last statement, the most critical factors of safety calculated range from 1.52 to 1.87. There's one critical factor of safety for each failure mode, not a range. Okay, that leads us to the critical failure surface once we have identified the critical cross section. There are 3 main failure modes: translational, rotational, and infinite. So the top diagram shows the translational failure mode, where you have strong material moving along a weak material, and the weak material could be the geosynthetics. A rotational slide is shown in the lower photograph image, and the slip surface is a circle or part of a circle. And generally we encounter circular or rotational failure surfaces when we have homogeneous material. So if you have a big discontinuity between the upper material and the lower material, it generally will not be a circle. The last mode is infinite block, and I'll show you some illustrations of that. So here's translational. This is a cross section that shows the liner system, the geosynthetic liner system along the base of this particular landfill. Here's what it looks like in actual practice. The cross section that you just saw was cut through this slope right here, and underlying it is the geosynthetic liner system. Here's an example of rotational. These are slip surfaces for homogeneous and isotropic materials. That's when a circular or rotational surface will develop. Here's an example of a rotational failure in the field, a industrial waste facility failing on a medium to soft clay underneath of it in a circular or rotational fashion. So that brings me to infinite slope or an infinite block. This is a good analysis for liner systems, geosynthetic cover systems, and they generally involve homogeneous material. It's a fairly simple analysis because a block, the slope is modeled with a block, as you see in the diagram. There's no resistance in front of the block, so you're really just evaluating the shear resistance along the base of the block versus the weight of the block tending to move it down slope. So the factor of safety is the resistance along the base divided by the weight tending to push the block down slope. So that leads to some very representative field conditions, such as you see on these three photographs. The first photograph in the upper left is during construction of a geosynthetic composite liner system. The granular material was placed on top of the cushion geotextile that you see here, the geomembrane underlying the cushion geotextile, and the compacted soil liner below the geomembrane. The granular drainage material was pushed from the top down, so this was an unbuttressed placement of fill, just like an infinite slope, and you can see the geomembranes torn right in this area because the resistance was less than the driving force. The other two examples are similar cases in which failure at this point had not occurred. You can see in the upper right where my pointer is, fill material is being placed over top of this PVC geomembrane from the top down, and the outside or front edge of this fill material is essentially like an infinite slope analysis. Here's a similar case, and that's for a bottom liner system. Here's a similar case for a final cover system where the cover soil is being placed on top of the polyethylene geomembrane from the top down, and that basically results in a similar infinite slope analysis. So those are the three main modes. We can have those modes present in a single slope, such as this example. This is a diagram that shows the California regulations for landfill design. So the slopes can be as steep as 1 to 1.75 on one, and they can be as flat as 3 to 1. If you use 3 to 1, you don't have to perform a rigorous slope stability analysis, but if you go steeper, you must have benches, and the bench is every 50 feet. If you have a bench slope like this, you have a number of different failure surfaces that you have to check. So you could have a failure surface daylighting at each bench, as I'm illustrating with my pointer, another one at the second bench, and then one through the toe of the slope. The slip surface could also go down to the bottom liner system, where my pointer is, and out through the toe. And then finally, a failure surface could be circular or non-circular through the landfill, through the foundation material, and also out through the toe. Now, we could also have an infinite slope analysis for the cover materials that are placed on this 1 to 1.75 slope, where my pointer is. And so this is an example of a situation where you could analyze all three of the failure surface modes: circular, translational, and infinite slope. So now that we've selected our critical cross-section, our critical failure surface for a particular mode, how do we actually calculate the factor of safety? So there's a variety of slope stability methods available. Here's a list of some of them. Many of you are probably familiar with Bishop's method, Yambu's method, Spencer's method, Morgenstern and Price. I want to focus on Morgenstern and Price and Spencer's method. They satisfy all conditions of equilibrium and yield reasonable values of factor of safety. The factor of safety is calculated by breaking the slope up into vertical slices, as you see in this little diagram. Here are the vertical slices. Each slice is treated separately by a free body diagram that you see below. The shear resistance along the base of the slice is estimated, as well as the weight of the slice, and the interslice forces on both sides of the slice are taken into account to calculate the factor of safety. The difference between all those slope stability methods that I just mentioned is really how the interslice forces are handled on the sides of this slice, and how the shear resistance is evaluated on the base of the slice. So let's look at these two methods that I mentioned, Morgenstern and Price and Spencer's method. So Morgenstern and Price's method came first, 1965, and Morgenstern and Price set up a function, theta, that's lambda times a function f of x, to represent the angle of these interslice forces from the toe all the way to the top of the slope. So these interslices forces vary as you go through the slope, and that's how this method will differ from Spencer's method. By doing that, the method becomes statically determinate, and thus a factor of safety can be calculated for Morgan, Stern, and Price's method. So you'll see in just a minute, this function f of x will be important in most slope stability software when you calculate the factor of safety. This term lambda that I'm pointing to is just a constant, and that's sort of a smaller part of the picture versus the function f of x. So in commercially available software now, you can use Morgan, Stern, and Price's method, which is great. It's a more rigorous method than Spencer's method, as you'll see in just a minute. And so I like using Morgan, Stern, and Price for both circular and non-circular slip surfaces because the interslice force angle theta varies from the toe up to the top. So in most commercially available software, you have selections for the interslice functions that I'm pointing to. So one particular software package has 4 different options: trapezoid, half sine, clip sine, which is the half sine, but all the function is above 0. And then the user can define their own function if they prefer. The 3D software, one commercial package allows 2 interslice functions for Morgan, Stern, and Price, half sine and constant. When you use Morgan, Stern, and Price, you should calculate factor of safety using all of the options and then use that option that yields the lowest factor of safety for that particular failure mode. So if half sine gives the lower value of factor of safety from trapezoid and clip sine, that would be the reported factor of safety for, say, the translational failure mode. So let's turn to Spencer's method. Spencer comes along 2 years after Morgan, Stern, and Price. Remember, this is 1967, which is a little while ago. And in 1967, you didn't have an iPhone or a laptop that could run sophisticated limit equilibrium analyses. So Spencer said, boy, we've got to simplify this problem a little bit, especially because Spencer's method can be done by hand, calculate the factor of safety by hand fairly easily. So Spencer said, instead of having theta as a function, theta is going to be constant from the toe to the top of the slope. Generally, that angle of theta is 1/2 of 0, or 1/2 of the slope angle, basically 0 to the toe to the slope angle divided by 2. And that's a rough approximation of the theta used by Spencer's method. So whether you're on a vertical slice near the toe or the vertical slice near the top of the slope, you will still be using the same theta. I'll make up a number, 12 degrees for your interslice resultant force. So that was a great simplification, and Spencer's method was used for decades because it is a good method. It satisfies all conditions of equilibrium, horizontal and vertical force equilibrium, as well as moment equilibrium. But now that most commercial software allows Morgan, Stern, and Price's method to be used, it's coded, it's been verified with numerical analyses, the best method to use is Morgan, Stern, and Price's method. And so accuracy of stability methods for circular failure surfaces, you could use Morgan, Stern, and Price's method. Bishop's method also works well for circles. For non-circular failure surfaces, Morgan, Stern, and Price, again, is a good method. Spencer also works, but if you're going to use Spencer's, you might as well just use Morgan, Stern, and Price's method. So the mechanics are fairly well understood for calculating factor of safety. Generally, you can be plus or minus 5% of the right answer from a numerical method. So really the uncertainty in the stability of geosynthetic line slopes is getting the geosynthetic interface strength or material strengths right. And that'll be a topic of a future webinar. But how would we present the results of the slope stability analysis. This is a diagram from a consulting report that I think does a really nice job of summarizing a slope stability analysis. In the lower left, here's a table that shows you the input parameters, so you don't have to go dig through the input files. The input parameters are right there. They analyzed non-circular or translational slide right here. They analyzed a circular surface as well. They report the critical factor of safety for both of those failure modes. They also give you a nice diagram at the top of the picture of the liner system and the geosynthetics involved, so the user or agency reviewing the permit application can quickly see where the possible weak links are and where the possible slope movement may occur. And then finally, in the upper left is the results of a seismic permanent displacement analysis, also called a Newmark displacement analysis. The yield acceleration or yield coefficient is estimated for each failure surface. That is used to then estimate the permanent displacement that could occur for the design ground motion for this particular facility. So this is a nice way to summarize both the static and seismic slope stability results. Okay, so let's now turn to infinite slope. This is a fairly straightforward analysis. The factor of safety is given by this expression here, weight times cosine beta times tangent of delta. Delta is the interface friction angle for the geosynthetics. I use delta instead of phi. Phi is generally used for soils, so you'll see in these next couple slides, delta is used for geosynthetic interface friction, and A is used for adhesion instead of C for cohesion in soils. So adhesion and delta. So slope angles beta, here's the block of the infinite slope. There's no buttress, no tension allowed or compensated for in the geosynthetics. The failure surface is, say, the geomembrane interface in a final cover system. So now we can add adhesion, and there's the A term for adhesion. So if this was soils, that would be a C for cohesion, and the factor of safety can be calculated. So what happens when we add water to a final cover system? Water builds up on top of the geomembrane. As you see here, we get H sub W, and now H sub W reduces the effective stress reacting on the geomembrane. So notice gamma H minus the water pressure, and that reduces the resistance. And so now with these very simple expressions, you can create a spreadsheet and quickly evaluate for your particular site the effect of adhesion, the effect of delta, the effect of water, and of course the effect of slope angle. So here's such a graph. This is the effect of water and delta on calculated factor of safety, which is along the vertical axis. So you can see the factor of safety ranges from 1 to say 1.6. Each line corresponds to a different delta. So depending on the geomembrane selected, you would have a different interface friction angle, delta, and you would measure that in laboratory direct shear test, either using ASTM D5321 or 6243 if you also want to include a GCL. So the interface friction angle ranges from 20 to 28. You could come in and see if the water depth is 10 inches, your factor of safety would be less than unity, and that would not be stable for a delta of 20 degrees. So if you thought 10 inches of liquid would build up on the geomembrane in the cover system, you'd have to go up to a much higher interface friction angle to reach a required value of 1.5. That delta would have to be at least 28 to 30 degrees up in this area of the chart. But with these simple expressions, you can quickly develop spreadsheets like this for a particular site and specify the geosynthetic materials accordingly. Of course, geosynthetics can also be used to drain the water from the cover system. Here's some examples of geosynthetic drainage composites that can be installed above the geomembrane and thus not allow the water level or liquid level to rise to 10 inches. The infinite slope analysis was modified by Nevin Matasevich in 1991 to include a seismic coefficient, so you can also use a simple infinite slope analysis to look at the pseudostatic factor of safety. The seismic coefficient is denoted here by K sub S, and you see it in the numerator and the denominator. It can also be solved to calculate the yield acceleration or yield coefficient for your permanent seismic deformation analysis. Okay, so now let's turn to slopes with geosynthetic reinforcement. So the geosynthetic interface friction angle may not be sufficient to achieve a factor of safety of 1.5 for the slope angle that you would like to construct. So you can increase the stability of the slope by adding geosynthetic reinforcement. Giroux et al. 1995, and there are references at the end of this PDF that give you the specific citation to this method. Giroux et al. Proposed this somewhat lengthy expression, but bear with me, it's a fairly straightforward expression. So the first piece right here is tan delta over tan beta, which is the frictional component from the infinite slope analysis we just went through. So if I back up just a couple slides, here is the frictional component, tan delta over tan beta. You bring the cosine beta into the denominator, the W's cancel, and you're left with tan delta over tan beta. That's the frictional resistance for the infinite block. So in Giroux's method, there's the frictional component, first piece. Second piece is the geosynthetic adhesion. The next two pieces of the expression are for the soils. So notice phi and C in the next two quantities of the factor of safety. So these two pieces relate to the soil that's placed above the geosynthetics in the cover system. You estimate the friction angle phi of the soil and the cohesion, if there is cohesion of the soil in a cover system, which is rare. You would use these two components. And then finally, the last component of the factor of safety equation involves capital T for tension right here. So that capital T is the tension provided by the geosynthetic reinforcement that could be installed just above the geomembrane, and that's this dashed line right here. Above the geomembrane, the red is the length of the slope that we're going to use to calculate factor of safety, and that extra tension gives us a higher factor of safety because notice T is in the numerator and thus would increase the factor of safety. So if I back up to this photograph, if you look closely, these are geogrids running down this slope, and this bulldozer is placing cover soil downslope, which is the non-preferred way to go because the leading face of this cover soil is not buttressed. Generally, it's better to place cover soil from bottom to the top. But with the geogrid reinforcement, that's giving the slope some additional tensile resistance. So the slope can be steep and also the cover soil can be placed top down. So the next two or three slides give some worked examples of how you can include geosynthetic reinforcement in your slopes. So here's the design example. It's a 3-to-1 slope in the upper left. The cover soil has a unit weight of 115 pounds per cubic foot, 0 cohesion, and a friction angle of 30 degrees. The geomembrane has a interface friction angle of only 14 degrees and no adhesion. And in this particular example, there's no slope reinforcement, so we're really just seeing where we are in terms of factor of safety. So if I use this Giroux et al. Expression, the adhesion term drops out and the cohesion term drops out, and I'm left with the factor of safety. Oh, I'm sorry, the tension term drops out because there's no reinforcement. I'm left with the friction and the soil strength terms, and you plug in the numbers and you get a factor of safety of about 0.8. Clearly, that's unacceptable. It's less than 1. That means the slope will fail. So how can we use geosynthetic reinforcement to improve the stability? So you can work the problem backwards and solve for the tension or tensile resistance required to make that factor of safety greater than 1.5, if that's your design value of factor of safety. So if you solve those numbers, your tension required would be 24,500 pounds per foot. That's a very strong geosynthetic reinforcement product. Very rare. Generally, the commonly available geosynthetic products are less than 20,000, certainly less than 25,000 pounds per foot. So we could solve the problem again by using a more readily available geogrid or geotextile as the reinforcement. So that's what I did in this example, same slope. But this time I went into the Geosynthetic Specifiers Guide and picked out a commonly available geogrid with a tensile resistance of about 7,600 pounds per foot, or 7,590. Now I plug in 7,590 for T, and now you can back calculate what slope I could accommodate using a factor of safety of 1.5 and geogrid reinforcement of about 7,600. And you could see that my slope has to be less than 34 feet. And that'll yield a factor of safety of 1.5. If I have to go steeper than 34 feet, of course, I can increase the tensile reinforcement or increase the cover soil above 30 degrees, but 30 degrees is pretty high initially. Or I can use a different geomembrane that gives me a higher interface friction than 14 degrees. So this is a nice way to see all the components affecting the factor of safety, and then you can vary the components accordingly to achieve the slope height and slope angle that you desire. Okay, that brings me to two-dimensional versus three-dimensional slope stability analysis. Most analyses are performed are two-dimensional slope stability analyses, but I hope to show you that there are a lot of places where a three-dimensional slope stability analysis is important. In general, a 2D analysis assumes a plane strain condition such that when you take the cross-section through the slope, you're assuming it's infinitely wide in each direction such that the 3D effects are not influencing your factor of safety. So one such example could be this long straight levee that you see here in this photograph. If I take a 2D cross section through it, say right here, that slope is so infinitely long and there are no 3D effects that I have a representative value of the factor of safety using a 2D analysis. However, you could have slopes that look like this one, which I showed you earlier, where you have a corner, and now that's a big three-dimensional effect. And the three-dimensional factor of safety is always greater than the two-dimensional factor of safety. So we want to use a 3D slope stability analysis where the geometry has three-dimensional effects, there are three-dimensional pore water pressure concerns, or there are changes in shear strength, and that's in particular geosynthetic shear strength, which I'll show you in just a minute, that yield differences in factors of safety between two different 2D cross sections. So let's talk about slope geometry. There's the case on the right I showed earlier, and here's the plan view of the landfill design I showed you earlier, where the critical cross section was drawn through this concave portion of the slope. You could run a three-dimensional slope stability analysis and evaluate the effects of that concave slope fairly easily. And it will be a higher factor of safety than what you calculate using a two-dimensional analysis in this two-dimensional cross-section. Okay, the three-dimensional analysis is very similar to the 2D, except instead of vertical slices, we have vertical columns. And there's your vertical column. Now, there are many more interslice forces, as you can see around this column, but the analysis is basically the same. The only place you get shear resistance in the numerator of the factor of safety is the base of the column, and the driving is due to the weight of this column, and then of course the interslice forces weigh in. So here's a diagram that a recent PhD student developed that shows width to height of the slope versus the ratio of the 3D to 2D factor of safety. So the important thing to notice here is with a width to height greater than 6, generally the 2D and 3D factors of safety are very similar, within 10 to 15%. See, the ratio is about 1.1 to 1.15. So what does width to height mean? Width is the width across this translational slide. The height is the height of the slope in the back. So if that width to height is greater than 6, you can perform a two-dimensional analysis and not worry about 3D effects. As the width to height ratio decreases, notice that the ratio of 3D to 2D factor safety decreases, and it can be as high as 2.1. So the 3D factor of safety could be twice what the 2D factor of safety is. So this graph is a good range for seeing where the slopes you need to perform a 3D slope stability analysis for. Now notice the lines are different slope angles, 1 to 1, 3 to 1, and 5 to 1. 5 to 1 slopes have the biggest 3D effect because it's a flatter slope and it takes a longer distance for it to reach the same height. The longer distance means there's more side resistance acting on the slope than a steeper slope. So how do we calculate three-dimensional factors of safety? So the program that was used for a long time, developed by Aldrich Hunger at the University of British Columbia, Clara, is still available. We've recently modified it with Aldrich's Hunger's assistance, and that program's now called 3D DEM Slope. I know it's a weird name, but means 3D Digital Elevation Model Slope Stability. And that's basically Clara W, Clara for Windows, converted to a input that can utilize digital elevation models instead of different cross sections to define the 3D geometry. Just recently, Rock Science daylighted a beta version of slide 3. I think it's now commercially available. Here's an advertisement for slide 3, and that includes three-dimensional geometry in a translational slide, though it does not include side forces. Like here, when the sides of the slide mass go at or near vertical, a column cannot have its base on this vertical side, so it does not include side forces. You can also perform a continuum analysis to look at 3D slope stability, and some software that's available to do that, FLAC 3D, Plaxis 3D, and RS3, also available by Rock Science. So when do I use a 3D slope stability analysis? Probably one of the biggest uses is an inverse analysis of a slope failure. So here's an inverse analysis of a landfill slope failure. The slope had an angle of about 21 degrees. There was a weak clay layer underneath the slope that I'm pointing to, and the municipal solid waste slid out along that weak clay layer in a translational fashion. The slide mass is shown here in the upper right. The 3D geometry with digital elevation models is shown in the right corner. So here's the results of the inverse analysis. If I perform my inverse analysis using a 2D analysis using Morgenstern and Price, I would back calculate a friction angle for that clay underneath the waste of about 15 degrees. So notice factor of safety of 1, 15 degrees. Now, if I use Clara, which does not include side forces, factor of safety of 1, I mobilize a friction angle of 12 degrees or 20% different. If I do a true 3D analysis and I include the side resistances along the sides of the slide mass, and if I go back, you can see the curved nature of this particular scarp. So there were side forces generated when this slide mass moved out into the open excavation at the toe. I would mobilize only 10 degrees of shear strength for the clay underneath the waist. And the reason it's only 10 degrees is the effect of the side resistance along the mast as it moved out is taken out in the 3D analysis. So the true strength of the clay underneath the waist is 10 degrees versus 15, which is a 50% overestimate of the back calculated friction angle for the clay underneath. That's significant when you're designing the repair for the slope, because if you use 15 degrees, of course, you're overestimating the strength of the clay by 50%. So a good place to use a three-dimensional slope stability analysis is inverse analyses of slope failures. Another good application for 3D analyses is where we have a three-dimensional geometry. This is a case where a landfill is being expanded, and right down the middle of the landfill, right where my pointer is, on the right, the geosynthetic liner system had to be installed. On the left, the landfill was grandfathered, and there is no geosynthetic liner system. So if I take a 2D cross-section through the geosynthetic portion, I get a low factor of safety. But if I take a factor of cross-section through the grandfathered area, I calculate a very high factor of safety because there are no geosynthetics. So what's the right value of factor of safety? It's really a three-dimensional problem because the grandfathered area is not going to move without the geosynthetic portion and vice versa. So you can model this 3D geometry as you see in the lower right. The dashed green line is the transition from grandfathered to geosynthetic lined. There it is during construction, and using a 3D analysis gives you a overall factor of safety for that. Now, the way 3D slope stability analyses should not be used is here. And 3D analyses are gaining popularity, and so I'm seeing 3D slope stability analyses being performed, but being compared to required two-dimensional factors of safety. In general, the 3D factor of safety is greater than 2D because you take into account the side resistance. So you shouldn't use the 3D factor of safety to maximize your slope. In other words, you should use a higher factor of safety than 1.5 if you're going to perform a 3D analysis. So let me illustrate this with some diagrams. So with a 2D analysis, my slope can achieve a factor of safety of 1.5 with a 3-to-1 slope. But if I do a 3D analysis, I can still go higher and still meet 1.5. But I'm at a different level of safety now because I'm including side resistance in my 3D factor of safety, and I am not in my 2D factor of safety. So I have some inherent conservatism in my 2D factor of safety. Similarly, people are using a 3D factor of safety to increase the slope inclination, say from 3-to-1 to 2-to-1, and still only comparing that to a 1.5. You can come into this chart that I showed you earlier for your width to height, and if you calculate 1.2, say, is the ratio, you would multiply 1.5 by 1.2, and that's the 3D factor of safety you should meet. Here's some other suggestions for required 3D factors of safety. The first one is the one I just mentioned to you. Some people have said that's too conservative. It's the most conservative to use that figure. So notice I take the 2D factor of safety, then I subtract the difference between 3D and 2D and divide by 2D. So Any way you want to calculate a new 3D minimum factor of safety is great, but you should be using a value higher than 1.5. Okay, summary of 3D. 3D factors of safety are greater than 2D, so you'll always get a higher factor of safety. The main use is for inverse analyses. If you're going to use it for design, you need to use a factor of safety greater than 1.5. Rotational slides, you can use a weighted average of different cross sections to calculate your 3D factor of safety. But for translational slides, you need to use a true 3D analysis. Last topic is municipal solid waste shear strength. Two things I want to point out. For fresh municipal solid waste, as you see in this upper diagram, a good strength envelope is, say, 35 degrees and a cohesion intercept of 6 kPa. It's a stress-dependent envelope, so it flattens out as you go to higher normal stresses with, say, 30 kPa cohesion and a friction angle of 30. If you have elevated temperatures and thermally degraded waste, that drops significantly the friction angle to about 20. And that's the red dashed line. Okay, so to summarize, and then hopefully there'll be time for questions. To calculate factors of safety in limit equilibrium, I think you should use the Morgenstern and Price method, and most importantly, use the different functions that are available in most commercial software. Calculate factor of safety with these different functions, and then use the lowest factor of safety from whichever function as the factor of safety for Morgenstern and Price's method. If you use Morgenstern and Price, the uncertainty is really in the geosynthetics and the geosynthetics shear strength. This should be addressed using site-specific laboratory testing of the geosynthetics involved, and that's going to be a topic of a future webinar. Finally, three-dimensional slope stability analyses are really beneficial for looking at the effects of complicated geometry, inverse analyses of slope failures, and variability of pore pressure and shear strength across a slide mass, as I illustrated with a grandfathered area and a lined area. 3D analyses should not be used just to increase the factor of safety. What I mean by that is, just don't use a 3D factor of safety, find out you can create additional storage capacity or volume with a steeper slope and still meet a 2D factor of safety 1.5, because you are no longer at the same level of safety as a two-dimensional analysis with a factor of safety of 1.5. Here's a list of the references that are referred to in the presentation and some extra references. Here's the Giroux et al. 1995 reference. Here's the waste shear strength reference that I just touched on. And contact information is shown here. If you would like a digital certificate emailed to you, please contact Jessica, who's listed right here on the slide. And hopefully, Andy, we have some time for questions.
Yes, Tim, we do, and I've been getting several of them come in here, so I'm kind of filtering through them right now. I'm going to bring those up here in just a minute. So I would say, anybody on the line, if you have questions, now would be a good time to ask those via the text portal on the right-hand side of your presentation screen. And I'm going to start going through a few of these. We've got about 10 minutes or so, I think, or a little less than 10 minutes to get through them. So the first one, Tim, was a good one from Nicholas Rocco. Basically said that 3D effects should be considered if necessary, but what's your opinion on whether the higher end 3D slope stability analysis will ever really become the state of practice and required by regulators?
I think they will become required. If your slope width is less than 6, there is a significant 3D effect. The real rub right now is regulations report a factor of safety that has to be met, for example, 1.5, but in the fine print, it doesn't say that that's a two-dimensional factor of safety. So what I think is going to change here in the real near future is regulations are going to say a two-dimensional factor of safety greater than 1.5, or a three-dimensional analysis with a factor of safety greater than some number. I'll make up a number, 1.7, 1.8.
Sure.
Hopefully the regulators won't be that specific because the value depends on the width to height ratio of the slope.
Yeah. No, that makes sense. So that's a pretty good segue into the next question, Tim, from Mike Feeney, that says he asked you to review again why the 3D factor of safety should be greater than the 2D factor of safety. Mike thought that it would have been the opposite since the 3D accounts for more forces.
That's a great question, and I sort of ran over that really quick. So in a slope, when you take a 2D section, it's saying there's no resistance left or right. With the 3D analysis, we get resistance on the sides. So if the width height is so wide, that resistance on the sides is a small portion of the entire resistance along that entire slope. So you can see as the width to height ratio gets smaller, the importance of the sides goes up.
Sure. So again, just for my edification as well, what do you think an appropriate factor of safety for 3D design would be?
I would go back to this chart that's on the screen, and it's a quick way to get an estimate of, you go in with your width to height right there. And so let's say we have a 3-to-1 slope, and we're at a width to height ratio of 4. So it would be 20% higher. So 1.5 times 1.2, that's about 1.7, almost 1.8.
Okay. Yeah, that sounds reasonable. Some good questions there. Chris Lynch asked, he'd be interested in your opinions on the differences in terminology between back analyses and inverse analyses.
They're used interchangeably, and I'm sure I'd used it interchangeably. I think the common trend now is to call it an inverse analysis, because we're basically inverting the analysis to estimate the strength instead of estimating the factor of safety.
Okay. This was a great question, and I'm interested to hear your opinion on it, Tim. What's your opinion on it? 3D analysis effects on modeling geomembranes with a hole on the upstream face of a dam. Can you envision that?
So that sounds like it's more of a seepage question than a slope stability question.
It might be. Yeah, we might have to get it was Sarper was his name, and I know he's not on audio, but if you hear that, Sarper, if you want to again maybe clarify a little bit on that question, and we'll come back to you on that. So this one, I might also see what you think about this question, Tim. So David Kreger asked, why do geosynthetics require site-specific testing if they're manufactured separately? I don't know. I guess what he's meaning is, or why are you doing redundant quality control testing on site if it's already been done by at the manufacturing facility?
A couple reasons why the testing must be site specific. First is generally a lot of manufacturers do not perform shear tests on their products. So second is the products that are put together for the liner system come from different entities. So one company may produce the geomembrane, one produces the geosynthetic textiles or the geogrid or what have you. So they all have to be put together and tested either single interface or multi-interface testing. Second is there are site-specific soils involved, whether it's the subgrade or the drainage media above it. And so it is site-specific configuration of the geosynthetic lining system.
Okay, that makes a lot of sense. I think we're getting close to our time, but we certainly don't want to stifle any questions. So please feel free to stay on, and we'll get to the rest of the questions. I know that if anybody had anything they needed to have a hard stop at 1 o'clock, they're certainly welcome to, but we'll stay on for a couple more minutes to continue answering questions. I didn't get any more clarification from Mr. Dimmerdogen, but I don't know, Tim. What do you think if there was if you had a breach or a hole in an upstream face of a dam and you started to have seepage that caused a rotational failure, would you be able to address that in a 3D analysis?
Well, it would be a 3D seepage analysis, and those are readily available. There's commercial available 3D seepage software that could easily handle that. No problem.
Okay. And again, for those of you that have asked, this presentation will be available as an email to attendees. I believe it will also be available online at either the GMA website or the Fabricated Geomembrane Institute website. We'll definitely make sure that that is available for everyone that attended today. I think that's all the questions that I see. We really appreciate your time in answering those, Tim. I thought it was a great presentation, and many people thanked you and said that it was a great presentation. So before we wrap up, I'd like to just mention some ways to become more involved with the Geosynthetic Materials Association. One of the great new initiatives that we're starting this year is kind of a refocus on the GMA Environmental Focus Group. We're going to be holding a meeting in June, date and time to be announced, of the GMA's focus group that discusses the use of geosynthetics in environmental applications such as coal ash, solid waste management, agriculture, aquaculture, mining, oil and gas. A great opportunity to get involved with GMA, learn a little bit more about geosynthetic materials and how they're positioned for use in these environmental applications. So I'm actually the chair of the GMA's Environmental Focus Group, and I'd be happy to answer any questions. Anybody's welcome to contact me for more information. So again, the recording of this webinar will be emailed to you later in the week, along with a copy of the PowerPoint. And we really thank you, Dr. Stark, and thank everyone else for attending today.
Thanks, Andy.